Hello everyone, welcome to this lecture session of the course Engineering Thermodynamics. In this particular lecture, we will continue our discussion on the concept of heat engine. Okay, so heat engine, I have started a discussion in our previous lecture, and I have told you that heat engine is a device which allows us to have positive heat and positive work interactions whenever our thermodynamic system is operating in an cyclic manner. Okay, so this particular heat engine, whatever I have demonstrated in the previous class, that is based on the piston cylinder arrangement. Okay, so that is particularly based on our actually closed system. Now we can also employ the number of steady flow devices. Okay, and with the help of these number of steady flow devices also we can actually achieve this heat engine process. It means we can achieve conversion of heat into work in a cyclic manner having positive heat and work interactions. Okay, so let me demonstrate this type of device. So what we will be doing over here, we will be having one heat exchanger. Okay, so we will be having over here one heat exchanger, and that particular heat exchanger we call as nothing but our boiler. Okay, so what we will do, we will try to supply some working fluid from here into the heat exchanger, into the boiler, and this boiler will be actually connected to some source of heat. So over here we will be having some heat source. Okay, so what basically this heat source will be doing, it will be supplying certain amount of heat. Let us consider that this heat source is maintained at temperature TH, and the amount of heat it is supplying is say Q1. Okay, so now what will be happening after this particular device heat source has given the heat to the working fluid. So inside we are having working fluid, and that working fluid we are considering that say it is in the close to the saturated liquid state. So if this is close to saturated liquid state, what will be happening? This particular working fluid, while we will be adding the heat, this will undergo through phase change process. Okay, so somewhere over here at the outlet we will be getting vapor phase, complete vapor phase, and now we will provide the heat in such a fashion so that we are having either saturated vapor or we are having some superheated vapor over here. Okay, so at the exit of the boiler we will be having nothing but complete vapor phase. So let me say that the point which I am getting, thermodynamic state of the substance which I am getting at the exit of the boiler, that let me call as nothing but say thermodynamic state 3. Okay, now what I'll be doing, I'll be now taking another device, and that another device is nothing but our turbine. Okay, so whatever this vapor phase we are having, this vapor phase we try to have at nothing but high pressure and high temperature, and this vapor phase then we will be expanding over a turbine, and from the turbine we will be getting work at the rate of W dot T. Okay, so this vapor phase actually I have expanded on the turbine. Now what will be happening from the exit of the turbine? Obviously we may have either exactly the vapor phase, or we may have mixture of liquid plus vapor, but whatever our state 4 will be having, that state 4 will be having nothing but less pressure in comparison to that of pressure at state 3. So our P4 will be less in comparison to P3, because in the turbine work will be done at the expense of the working fluid pressure. Okay, so this is point number 4. After point 4, what we will be doing, whatever the vapor we are getting, so at this stage either we will be having vapor or we may have mixture of liquid plus vapor, but obviously majority of vapor we will be having over here. After that, what we will be doing, we will be connecting one more device. That particular device we call as nothing but our condenser. Okay, so in this condenser, what we will be doing, whatever the vapor or liquid plus vapor we are having, that will be actually exchanging the heat. Now it will exchange the heat, but it will exchange the heat with some heat sink. So we will be having some heat sink at temperature TL which is less than TH, and it will exchange the heat with that heat sink. Okay, so now if you see, this turbine inlet and boiler are actually in the same pressure line, because in between these two we don't have any device where we will be having actually change of pressure. So these are at the same pressure line, and if you see this below at the exit of turbine and this particular condenser, these are nothing but at the same pressure line, and we already know that pressure P4 is less in comparison to P3. Okay, so if I say that at the exit of the compressor, if I exit of the condenser, if I say at the exit of the condenser I have say stage 1. So my stage 1 pressure P1, and if I say at the inlet of the boiler we have nothing but thermodynamic stage 2, so my P1 is actually less in comparison to P2. So now what I have to do in order to complete the cycle, I have to actually employ over here one more device. That particular device we call as nothing but our pump. So I'll be using one pump over here, and what that particular pump will be doing, that will be actually compressing our substance. Okay, so at the inlet we are giving some low pressure substance. Now this pump will take some mechanical work, so it will be taking some pump work as input work, and it will be actually compressing our substance. So finally we will be finding some high pressure substance, so it means my P2 will be nothing but greater than P1. Okay, so this particular type of cycle we can have. So if you try to see in this particular cycle what we are having, if I have to take individual this particular heat exchanger into consideration, it is nothing but a steady flow process. If I have to take individual turbine, once again it is a steady flow process. Individually condenser and pump are also steady flow devices. Okay, and all together what we have done, we have actually combined the different steady flow devices, and we have combined these in such a fashion so that as a whole we are getting our thermodynamic cycle, and that thermodynamic cycle is actually getting Q1 amount of heat from a heat source. Okay, and it is rejecting Q2 amount of heat to a heat sink, and it is actually doing WT amount of work, and it is requiring WP amount of work at the pump inlet. Okay, so now if I have to analyze this entire cycle, if I take entire thermodynamic cycle as my control volume, as my system, so I can see that in my entire cycle we are not having any mass interaction. If I take individual devices, then obviously we are having the mass interaction, so it means our individual devices are nothing but the open systems. But if I take overall cycle, except for the heat sink and heat source, then my system will not have any mass interaction, and only interaction we will be having heat and work interactions across the boundary of the system. So it means as a whole, if I take this entire thermodynamic cycle, I can consider this as nothing but my closed system. Okay, so for the complete thermodynamic cycle, now let me write down the equation, energy equation for this thermodynamic cycle. So if I consider this thermodynamic cycle, it will be nothing but a closed system. So we know that for closed system, del Q minus del W is nothing but equal to delta U. Okay. Now, if this is a cyclic process, then we have to write over here cyclic integral del Q minus cyclic integral del W, and this also has to be cyclic integral, and cyclic integral of du will be equal to 0. Okay, because for cyclic process initial and final point is 0, so that's why our change of property will be 0. So I'll be finding that cyclic integral of del Q equal to cyclic integral of del W, and finally I can say that my Q1, so heat is being added at the rate of Q dot 1, so Q dot 1 minus Q dot 2, that is my net heat transfer, that is equal to nothing but equal to W dot T, which is the work done by the system, minus W dot P, which is the work supplied to the system. Okay, so this is my nothing but net work done, and this is the net amount of heat transfer, net rate of heat transfer. So I can say that my whatever the net output work I am getting, that is nothing but equal to Q1 dot minus Q2 dot, where Q1 is the amount of heat added, and Q2 is the amount of heat rejected. So it means once again I can say that I cannot convert complete Q1 amount of heat into equivalent amount of net work output. Okay, so what we are doing basically, whatever the net work output we are getting, that is nothing but the amount of heat added minus some amount of heat rejected. Okay, so it means that heat cannot be converted 100% into work. So complete amount of heat cannot be converted into equivalent amount of work. That is something which we are able to see from this particular second system also. Okay. This particular heat engine is nothing but a basis for our second law of thermodynamics. So now if I talk about second law of thermodynamics, okay, so for the second law of thermodynamics, what we are having actually numerous ways to demonstrate the different statements of second law of thermodynamics. But in particular, if we talk about second law of thermodynamics, is referred to as Kelvin-Planck's statement, and second statement is particularly referred to as Clausius statement. Okay, so our Clausius statement is actually having a close correlation to that of our refrigerator and heat pump, whereas our this Kelvin-Planck statement is actually specifically related to our heat engine devices. Okay, so let me specify, because already we have completed the discussion of the heat engine. So let me specify that what is our Kelvin-Planck statement. So as per the Kelvin-Planck statement, what we are having, we cannot construct a device. So it means it is impossible to construct a device which will operate in thermodynamic cyclic manner by exchanging heat with a single thermal reservoir. Okay, so it is impossible to construct a device which will operate in thermodynamic cyclic manner and produce positive net work output by exchanging heat with a single thermal reservoir. Okay, so if you see, in case of my heat engine, what I have just now shown you, that I'll be having one heat source with temperature TH, which will be greater than TL, and then below I'll be having one heat sink having temperature TL. Okay, and in between this heat sink and heat source, we will be having actually our main device. That device we are calling as nothing but our heat engine. Okay, so what were the important components inside heat engine? Inside heat engine, we were having nothing but our boiler, then we were having turbine, then after the turbine we were having condenser, then here we were having nothing but our pump. Okay, so these all are our different components which we can actually all together join, and we can call these as nothing but our heat engine. So if we place our heat engine in between two thermal reservoirs, so the very first thermal reservoir is actually supplying Q1 amount of heat, and second thermal reservoir is actually taking Q2 amount of heat from this working fluid, and while this heat is being exchanged, during that time this heat engine is actually giving us some W dot amount of output work. If I say this net work output as W dot net. Okay, so as per the Kelvin-Planck statement, we cannot have system where we are having this Q2 equal to 0. So if we are saying that our Q2 is equal to 0, so this type of system is actually not possible. Okay, so we cannot have a device which will operate in thermodynamic cyclic manner and will only exchange the heat with a single thermal reservoir and produce some net output work. Okay, so now while we are having heat engine, obviously when we are having any system, we try to define some parameter which we call as nothing but the efficiency of that particular device. Okay, so in this particular system, what we are doing, we are converting actually heat energy into work. Okay, so when we will be talking about the efficiency of this particular device, in general, the definition of efficiency is nothing but our output divided by input. Okay, so when we will be defining the efficiency, let us define efficiency with symbol eta. So when I will be defining efficiency for this particular heat engine device, what will be my output? So from heat engine, what is the purpose of heat engine? Okay, the purpose of heat engine is to produce some net positive work output, and for obtaining that net positive work output, what we are doing, we are supplying certain amount of input heat. Okay, so that's why what will be happening, our efficiency will be nothing but output divided by input. So efficiency of the heat engine will be equal to, in case of heat engine, our desired output is nothing but the amount of work done which we are getting from our system. Okay, so that's why my rate of work done will be W dot net, and in order to obtain this rate of work, what we are doing, actually we are supplying this Q dot 1 amount of heat to the heat engine. So that's why my input will be nothing but Q1 dot. Okay, so now if you apply over here for this cyclic process, if you apply the first law of thermodynamics, already I have told you that W dot net will be nothing but equal to Q1 dot minus Q2 dot. Okay, so now I can write my efficiency of the heat engine as nothing but equal to work I can replace with Q1 dot minus Q2 dot divided by Q1 dot. So finally, I'll be finding my efficiency of the heat engine is nothing but equal to 1 minus Q2 dot divided by Q1 dot. Okay, so just now I have told you, as per the Kelvin Planck statement of second law of thermodynamics, that it is impossible to construct a device which will exchange the heat with single thermal reservoir and produce net work output by operating in a cyclic manner. Okay, so that's why if we are considering that our Q2 dot is 0, so if Q2 dot is 0, in that case, what will be happening? The efficiency of the heat engine will be equal to 1, and which will be nothing but equal to 100%. But this particular thing violates the Kelvin Planck statement of second law of thermodynamics. So because of that, what will be happening? Always we will not be having any heat engine which is having efficiency equal to 100%. So that's why efficiency of the heat engine will always less than 100%. Okay, because we have to have some positive amount of Q2 dot, then only our Kelvin Planck statement of second law of thermodynamics will be applicable, and once second law of thermodynamics is applicable, then only our process will be feasible. Okay, so for a practical process, for a feasible process, always the efficiency of the heat engine will be less than 100%. Okay, so now if I talk about, already in our earlier lecture, I have given you the example of different heat engine devices. So one of the heat engine device is nothing but our coal-based thermal power plant. So the efficiency of coal-based thermal power plant is around of the order of 50 to 55%. Then we are having internal combustion engine. So if we talk about internal combustion engine, our gasoline engine, so the efficiency of gasoline engine is around 30 to 35%. And if we talk about the efficiency of the diesel engine, that is something around 40 to 45%. Okay, so that's why the efficiency of our devices, heat engine devices, is actually low. So it means you can see that the most efficient device which we are saying, that is also only able to convert 50% of the heat into work. Okay, and now what we will be doing, we will be now starting our discussion on another kind of device. That particular kind of device is something which is known as a refrigerator. Okay, so refrigerator is nothing but it is the reverse of heat engine. So if thermodynamically we try to see, thermodynamically it is nothing but reverse of heat engine. Okay, And what is the purpose of using a refrigerator? The purpose of using a refrigerator is to facilitate the transfer of heat from low temperature to high temperature. Okay. So that is something which we say, that a refrigerator is a device which is nothing but thermodynamically, if we try to see, it will be the reverse of the heat engine, but it facilitates us to transfer the heat from low temperature to high temperature. Okay, so while it is doing so, basically it is doing against the laws of the nature. So that's why it will be requiring some work input. Okay, so it will require some work input to do so. So in order to facilitate this transfer of heat from low temperature to high temperature, because we are doing this against the laws of the nature, so that's why it will be requiring certain amount of work input. Okay, so now let me explain the process of refrigerator. So in case of refrigerator, once again, the process will be thermodynamically similar to that of heat engine, but the difference will be coming that it will be operating in reverse manner. Okay, so what we are having over here, this TH is greater than TL. So this is our heat source and this is our heat sink. Okay, now in this particular case, what will be happening? We will be having actually transfer of heat in the opposite direction. Okay, so in between, say if I say I have some device, and that particular device I am calling as nothing but my refrigerator. Here I have some device which I am calling as refrigerator. So in this refrigerator, I will be having some components, and these components will be arranged in such a fashion so that these will be transferring the heat from this TL temperature, which is low. So I will be having QL dot heat addition from this particular, and it will be actually rejecting some QH dot amount of heat to the high temperature thermal reservoir. Okay, so in this particular refrigerator device, now we have to arrange different components which will facilitate this process to happen. Okay, so what we will be doing over here, we will be considering one heat exchanger. So let me consider one heat exchanger over here, and this particular heat exchanger we call as nothing but our evaporator. Why we call evaporator over here? Because while our fluid working medium enters at the inlet of the evaporator, that working medium is either in the saturated liquid or in liquid plus vapor regime. Okay, so we will be having our working medium either in saturated liquid or liquid plus vapor regime, and this working medium, then working fluid, will be actually taking some heat input. So because of the heat input, actually it will be either becoming saturated vapor or superheated vapor. Okay, so after addition of the heat, either it will become saturated vapor or it will become superheated vapor. Okay, so now let me say that at this particular point my thermodynamic state is 1, and at this point my thermodynamic state is 2. Okay, so now after this, what we will be doing, we will be passing this particular working medium through a device, and that device we call as nothing but our compressor. Why I am calling it as compressor? Because now our working medium is actually in the gaseous phase. So while we will be compressing some working medium which is in the gaseous phase, we call our device as nothing but compressor. Okay, after that, what will be happening? So we are compressing gaseous phase over here. That's why we will be calling this as nothing but our compressor. Okay. So now at the outlet of the compressor, what I will be having? I will be having some thermodynamic state, say 3, and this state 3 will be having actually high pressure P3 in comparison to that of P2. Okay, so because we are having a device over here, this device is nothing but our compressor. So this will be requiring certain amount of work input. So I'll be having W dot C as nothing but the work input to the compressor. Okay, and this compressor from 2 to 3, it will be actually increasing the pressure of the working medium. After we are having increase in pressure, obviously our temperature will also be increasing with increase of the pressure. So after that point, what we will be doing now, our working medium will be once again in the vapor state. So it may be superheated or it may be saturated vapor. Okay. Now what we will be doing, from this vapor actually we will be removing the heat. So while we will be removing the heat, this vapor will be converting into nothing but my liquid phase. Okay, so this vapor will be converting while we are actually removing the heat from the vapor, it will be converting into liquid phase. So any heat exchanger in which liquid converts, a vapor converts to liquid, we call that as nothing but our condenser. Okay, and after that, what we will be doing now, we want to decrease the pressure of this liquid. So for decreasing the pressure of liquid, I can now use some expansion device. Okay, so throttle is my one of the expansion device. So let me use over here some throttling device. Okay, so I am using throttle as my expansion device, which will be actually now decreasing the pressure. So if I say state 3 was at this point at the inlet to the condenser, if I say I have say thermodynamic state 4 at the outlet of the condenser and inlet to throttle, so my P4 pressure will be more in comparison to pressure P1, because in case of throttling expansion device, we will be having actually decrease of the pressure. Okay, so while pressure will be decreasing, we operate this throttle in such a fashion for our refrigeration applications that with decrease of pressure, our temperature is also decreasing. Okay, so this particular device, it is actually now facilitating the transfer of heat from low temperature to high temperature, and while this transfer of heat is happening, we are actually supplying some W dot C amount of work to our compressor. Okay, so this particular device is known as our refrigerator. Okay, so refrigerator is a very common device which we all see in our home appliances. Moreover, the principle of air conditioning unit is also similar. So in case of refrigerator or air conditioning, our motive is actually to cool the space. So whatever this low temperature thermal reservoir I am taking, this is nothing but our space which we want to cool. Okay, so this is our cooling space. Okay, so for example, in case of refrigerator, we keep some vegetables, fruits, etc. inside our refrigerator, which we want to preserve for long time. So we want to maintain their temperature. Okay, so that's why what we will be doing, our freezer unit and the inside area of the refrigerator will include this space. And in case of air conditioning unit, what we want to do, generally in summers, our outside medium is actually ambient is hot, and inside room we want to maintain at cold conditions. Okay, so that's why whatever our inside room is there, that will be acting as our space which we want to cool. Okay, so that we can do with the help of some input work. So you might have seen that in case of our air conditioning unit and refrigerators, we are having some compressor, and normally we connect that compressor to electrical supply. Okay, so we are providing some electrical input to that compressor. So basically we are providing the work in the form of electrical input. Okay, so now like I have defined the efficiency of heat engine, in the same way I have to also define the efficiency for refrigerator also. Okay, so if I talk about the refrigerator efficiency, so I have already told you that my efficiency is nothing but desired output divided by whatever amount of input we are supplying to achieve that desired output. So in case of refrigerator, what we are having a TH as our one medium, then in between we are having our refrigerating unit, and this refrigerating unit is actually receiving some QL dot amount of energy from our TL temperature, and it is rejecting QH dot amount of energy, and it is actually requiring some W dot C amount of work input. Okay, and in case of refrigerator, what will be happening, as I have already told you, so this will be this particular space over here, it will be my space which I want to maintain at the desired condition, and this TH will be nothing but our atmosphere. Okay, So if you see, in case of a refrigerator, we actually allow that heat which is rejected by the refrigerating unit, we allow that heat to go into surroundings. That's why if you see at the back side of your refrigerator, you are having some coil like structure. That coil like structure is actually called as the condenser of the refrigerator. Okay, similarly in case of air conditioning unit, what we do basically, we try to keep our evaporator into the space which we want to cool, and we try to keep our compressor and condenser unit outside the room. So that's why we are also, with the help of condenser, actually we are removing additional whatever the amount of heat which has to be rejected, that we reject that heat to our surrounding. So our surrounding, this heat source is nothing but our atmosphere, and the space which we want to maintain, that is actually our heat sink, that is TLA over here. Okay, so now efficiency, as I have told you, that efficiency is nothing but desired output divided by input. So in this particular case, our output is nothing but what we want to do. We want to cool this particular space. Okay. So if we want to cool this particular space, in order to cool this space, we have to remove some amount of heat. So we are removing Q dot L amount of heat from the space. So that's why this Q dot L will be my desired output. Okay, and in order to achieve this desired output, what is my input? The input is actually W dot C amount of work, W dot C amount of electrical energy which we are actually supplying to our refrigerating unit. So input will be my nothing but W dot C over here. Now if I apply the first law of thermodynamics, as per the first law of thermodynamics, I will be finding that Q dot L is the heat which I am adding to the refrigerator. So I am applying first law of thermodynamics considering only refrigerator as my system. So Q dot L, we are actually adding some heat into the refrigerator, minus Q dot H is the heat which we are rejecting from the refrigerator. That will be equal to nothing but net amount of work done. So amount of work done over here, we are having only the compressor work, because other side we have used throttling device which doesn't have any work interaction. So the only amount of work is W dot C, and this is also work done on the system. So as it is on the system, so that's why I'll be writing minus W dot C over here. So from here I'll be finding that W dot C will be equal to Q dot H minus Q dot L. Okay, so now if I substitute this over here, I'll be finding that output by input is nothing but Q dot L divided by Q dot H minus Q dot L, because I can replace W dot C by Q dot H minus Q dot L. Okay, and if I divide both sides by Q dot L, both numerator and denominator, I'll be finding 1 divided by Q dot H by Q dot L minus 1. Okay, so already you can see over here that my Q dot H is nothing but equal to W dot C plus Q dot L. So it means my Q dot H divided by Q dot L will always be greater than 1. If this is always greater than 1, now the particularly for the range, I have seen my output by input as nothing but equal to 1 divided by Q dot H by Q dot L minus 1. So particularly for the range where Q dot H by Q dot L is actually having value in between 1 to 2, during that particular value, what will be happening? My value of output divided by input will be actually going beyond 1. Okay, so this is one important point, that my output by input value will be more than 1, particularly when my Q dot H by Q dot L is actually having value in between 1 to 2. Okay. So this is one important point which we will be getting over here, that my output by input will be greater than 1, and that will be greater than 1 only if when our Q dot H by Q dot L is having value from 1 to 2. Okay. So now what we are finding, that for the case of refrigerator, our definition of efficiency, so output by input is nothing but the definition of efficiency. So our definition of efficiency is giving us some magnitude which is greater than 1. So it means our efficiency is becoming actually greater than 100%. So generally when we talk about efficiency, we limit our value of efficiency to 100%. Okay. However, for this particular device which we have considered over here as refrigerator, we are finding that our efficiency is actually going beyond the value of 100%. Okay. So in general, we are having the trend that we call that our efficiency is always less than 100%. So by considering this into consideration, what we say, we define this output by input as performance parameter for refrigerator, and we call this as nothing but coefficient of performance. Okay. So because our value of performance parameter for refrigerator is actually going beyond the limit of 100%, and efficiency is a common parameter which we do not call, which we limit only up to the maximum value of 100%. So that's why what we do, we are calling over here the performance of refrigerator as nothing but with some another name that we are calling as coefficient of performance. In short form, it is referred to as COP, and generally it is given by symbol beta. Okay. So that's why what will be happening for a refrigerator, I'll be calling my COP of refrigerator as nothing but equal to beta, which is equal to Q dot L divided by Q dot H minus Q dot L, and I can call it as 1 divided by Q dot H by Q dot L minus 1. Okay. And the value of this beta can also go beyond 100%. Okay. So value of beta may be greater than 100%. It is not always true that always it has to be greater than 100%, but yes, it can be greater than 100%. Okay. So this particular device is actually referred to as our refrigerator. Now another device which is in principle identical to that of refrigerator, but is only having difference of difference of the desired output, whatever we want to achieve, that is called as nothing but our heat pump. Okay. So like in case of refrigerator, our motive was to maintain our system in the cold condition. In case of our heat pump, our motive is actually to maintain the system at temperature above than the surrounding temperature. Okay. So we want to make our system hot. We want to heat our system. So that's why what will be happening in case of heat pump, if I say this is my heat pump. So in principle, it will be exactly same to that of our refrigerator, but the only difference will be coming in terms of application. Okay. So if we see in terms of application, we will be having some Q dot H amount of heat which we are actually rejecting. So that Q dot H amount of heat will be actually supplied to our system, because now we want to maintain our system above than the surrounding temperature. Okay. And what we will be doing, we will be actually, in order to achieve this, we will be using, we will be taking some heat Q dot L from our surroundings. So over here, TL will be nothing but my surrounding atmosphere. So it will be my surroundings to the system. And obviously, if we have to make this process happen, what we have to do, we have to supply certain amount of work. So W dot C amount of work we will be actually supplying. Okay. So this particular system is actually applicable during the winter season. For example, in winters, what will be happening? Our surrounding temperature will be low in comparison to the system temperature. We want to maintain this system at the human comfort condition. So we want to maintain our room at human comfort condition wherever our outside surrounding temperature will be low. Okay. So this particular type of device is actually fairly needed for your rooms at IIT Mandi. So you will be finding that if you are taking classes in the month of December and January, outside we will be having temperature close to 2 degree or 5 degrees Celsius. However, inside temperature we want to maintain at 20 to 25 degrees Celsius at the human comfort condition. So that's why we require this kind of heat pump system. Okay. Now, if I do the thermodynamic analysis of heat pump, so in that case, what will be happening? Now I am to this heat pump, I am supplying Q dot L amount of heat, and Q dot H amount of heat is going out. and that is equal to nothing but minus W dot C because work is done on the system. So ultimately I will be finding W dot C as nothing but equal to Q dot H minus Q dot L. So first law of thermodynamics remains exactly same as it was in case of refrigerator. Okay, but for this heat pump, what will be happening now? We will be defining the COP of the heat pump. So COP of the heat pump is generally given by symbol beta dash. So beta dash will be nothing but equal to output divided by input. Okay, so what is our desired output in case of heat pump? In case of our heat pump, what we want to do, we want to maintain the temperature of this particular system, which is at higher temperature. We want to maintain its temperature, okay, above than the surrounding temperature. So that's why in order to maintain this temperature, we have to actually supply certain amount of heat. So whatever this Q dot H amount of heat we are supplying to our system, that is actually our desired output. Okay. So over here Q dot H will be my desired output, and in order to do so, we are actually supplying W dot C amount of work. Okay. So if I calculate the performance, beta dot will be nothing but Q dot H divided by Q dot H minus Q dot L, and now if I just write Q dot H divided by Q dot H minus Q dot L, and if I add Q dot L and if I subtract Q dot L, my equation will remain unaffected, and finally I'll be finding that my beta dash is nothing but equal to Q dot H minus Q dot L. I can take this as one term together divided by Q dot H minus Q dot L plus Q dot L divided by Q dot H minus Q dot L. Okay, so this first term is nothing but equal to 1, and this second term over here is nothing but the beta COP of a refrigerator. Okay, so this will be equal to 1 plus beta. So it means my COP of heat pump beta dash will be always equal to 1 plus COP of the refrigerator, which is operating within the same values of heat transfer rates. Okay. So that's why we can say from this particular equation that for a heat pump, COP will always be greater than 1. So beta dash will always be greater than 1 for the heat pump device. Okay. So now these two devices, heat pump and refrigerator, has given origination to second statement of second law of thermodynamics, which is referred to as the Clausius statement. Okay. So as per this Clausius statement, what we are having, as per this second statement, we are having that it is impossible to construct a device. It is impossible to construct a device which will operate in thermodynamic cyclic manner and produce no effect other than transfer of heat from low temperature to high temperature. Okay, so this is the statement of Clausius, that it is impossible to construct a device which will operate in a thermodynamic cyclic manner and produce no effect other than the transfer of heat from a substance having low temperature to a substance having high temperature. Okay, so what it means, we have seen in case of a refrigerating unit that we are transferring the heat, Q dot L amount of heat we are actually transferring from temperature TL, and we are supplying this heat to our medium at temperature TH with Q dot H rate, and while we are doing so, we are supplying some W dot C amount of work. Okay, so it means this statement says that it is impossible to construct a device for which only we are transferring the heat from low temperature to high temperature without having any other effect. Okay, so if we are saying if we are not having any other effect, it means this work has to be zero. But with zero work, it is impossible to construct. So that's why what we have to do, we have to supply certain amount of work in order to make this process feasible. Okay. So now if we see the definition of our coefficient of performance, so we know that our coefficient of performance is nothing but equal to Q dot L divided by W dot C. So as I have told you that if we are having W dot C equal to 0, under this condition what will be happening, my beta will be actually infinite. So this beta equal to infinite condition is actually impossible. That is something which is told by the Clausius statement. Okay, so only what we are having, we will be always having some positive amount of compressor work which will be acting as an input. Because of that, my value of beta will always be less than infinity for the practical system. Okay, so this particular statement is actually referred to as nothing but Clausius statement. Now, one important point I would like to highlight over here. So whatever the two statements we have seen for the second law of thermodynamics, both these statements are nothing but negative statements. So why these are negative statements? Because we are always finding out the impossible situation. We are saying that whichever condition or whichever situation is impossible, that we are actually stating over here. So that's why both these are nothing but negative statements. And one important point, for both these statements, we are not having any initial theoretical analysis. So fundamentally, both these statements are derived from experimental evidences. Okay, so people have tried to construct different kind of devices, and whatever their conclusions were there from the different devices, based on these conclusions, actually they were able to get these two statements. Okay, so the second important point, that both these statements are derived from experimental evidences and these are not having any fundamental basis. Okay, now one important point is there, that both these statements of second law of thermodynamics are equivalent to each other. Okay, so both these statements are equivalent to each other. So it means that if we are saying that one of the statement is failing, other statement will fail automatically. Okay, so because of that, let me demonstrate this one. So what I'll be doing first, so the meaning of equivalence is that if one of the statement is not applicable for some system, another statement will also not be true for that system. Okay, so what I'll be doing over here now, let me first consider that we are having a system for which Clausius statement is not applicable. So we are saying that we are having a system for which Clausius statement is not applicable, and if we are taking such a system, for that system now we have to demonstrate that our Kelvin Planck statement should also not be applicable. Okay, so what I am doing, I am considering that I have some heat source at temperature TH and I have some heat sink which is at temperature TL, which is less than TH. Okay, now I have, what I am doing basically, I am saying that my Clausius statement is not applicable. So it means I'll be considering that I have a refrigerator, and this particular refrigerator is actually taking some Q dot L amount of heat input, and it is not taking any work input. So W dot C is equal to 0 for this refrigerator. So because of that, what is happening now, I am transferring only the Q dot L amount of heat to my high temperature. Okay, so if I say that I have a refrigerator which is not taking any work input but only transferring the heat from low temperature to high temperature, in that case what will be happening, we are having nothing but the violation of second Clausius statement of the second law of thermodynamics. Now if I say that at the same point of time I have a heat engine also, and this heat engine is actually taking, say, Q dot H amount of heat, and it is rejecting Q dot L amount of heat, and it is doing some work output W dot net, and that W net will be nothing but equal to Q dot H minus Q dot L. Okay. Now, if you see this heat exchanger, this heat engine is actually exactly working as per the second law of thermodynamics, because in this heat engine, what we are having, we are exchanging the heat with two thermal reservoirs and we are producing some output amount of work. Okay. But one important point, if you try to see over here, that what we are doing for this heat sink, we are taking certain amount of heat from it. So Q dot L amount of heat we are taking from it, and at the same point of time Q dot L amount of heat we are adding also to it. Okay, so it means with this particular heat sink, we are not having any difference of energy. So the heat inflow and heat outflow to this reservoir is actually same. So because of that, what I can do, I can actually avoid this reservoir from my system, and directly I can connect my this Q dot L amount of heat to nothing but my refrigerator. Okay, so in that case, my equivalent system, if I redraw, I'll be finding that I'll be having some TH over here. Okay, now I have some refrigerating unit, and this refrigerating unit is supplying Q dot L amount of heat to high temperature. I have a heat engine also. So this heat engine is taking Q dot H amount of heat, and this heat engine is producing some W dot net amount of work output, and it is rejecting Q dot L amount of heat. But instead of rejecting that Q dot L amount of heat to our low temperature reservoir, we are actually passing that amount of heat to nothing but our refrigerator only. Okay, so over here only we are passing this Q dot L amount of heat. So now if you say our second reservoir is actually taken out of the system, and this heat engine is now only exchanging the heat with a single thermal reservoir in a cyclic manner, and it is producing some W net amount of work also. Okay, so what is the meaning of this? The meaning of this is that our Kelvin Planck statement is actually not satisfying over here. Okay, so it means that if we are considering that our Clausius statement is not applicable for a system, if we go by that and if we try to have an equivalent heat engine system over here, we will be finding that whatever the heat engine we will be getting, that will be actually violating the Kelvin Planck statement also. Okay, so that's why if we are having violation of any one statement, other will also be automatically violating. Okay, so this one particular demonstration I have shown you, that if Clausius is violating, we are finding that Kelvin Planck will be also violating. Now you can take one example other way, that initially you assume that your Kelvin Planck statement is actually violating, and then you show that Clausius statement will also not be applicable for your system. Okay, so this you try by your own, otherwise we will see in our